Look at it. So I'm telling about sun is concerned, we must have the knowledge about the transition involved in UV spectroscopy. First thing. Second thing, we must have the knowledge about the basic terms involved in UV spectroscopy. And third one, effect of solvent. And no doubt, we can say that when we consider the transitions, then we have to consider the lambda max value also. So take a look. This is the first question. In the UV visible spectrum, a diterpenoid exhibited a lambda max at 275 nanometer. The compound among the choices given below is, now there are four options. And let me remind you, as I told you that there are four options, out of which one is correct and three are wrong. So it is difficult for us to decide which is the correct options. And definitely it is difficult for the examiner to set three wrong options in front of one correct options. So we have to use our common sense to get the answer. So look at here. Here four options are there. And what is asked? That means out of the following compounds, which one shows the lambda max at 275 nanometer? Look at here. There are three fused rings in each of the options. And as we know that, if we consider the ring in which two double bonds are conjugated within the same ring, then such ring is called as homoannular ring. And for homoannular ring, what is the basic lambda max value? It is 253. Okay. And when we consider this ring system in which two double bonds are there, okay, but they are in the different ring, then, and they are conjugated, that means if the two double bonds in the system are present, but they are present in different rings and they are conjugated, then it is called as heteroannular ring. And for heteroannular ring, what is the basic lambda max? 214. Okay. So here what is asked? Which of the following compound shows the lambda max at 275? So out of these two values, that means for homoannular ring, lambda max is 253. And for heteroannular ring, lambda max value is 214. So which value is closer to 275? Definitely 253. So you have to search the option in which only one ring has the two double bond in a conjugation. And this will be the C. Third option is the correct one. Understand? Okay. Now, take a look at second option. Let me second question. The absorption at lambda max 279 nanometer. Epsilon value 15. Here epsilon value means here absorptivity. Okay. As the absorptivity increases, we can say that intensity of absorption increases. So look at here. The absorption at lambda max 279 nanometer in the UV spectrum of acetone is due to. In acetone, there is a carbonyl group. And this carbonyl group can show what? Pi to pi star transition as well as N to pi star transition. Both are possible in acetone. Okay. But pi to pi star transition requires higher energy as compared to N to pi star. And the transition which requires higher energy, definitely it has a lower lambda max. Okay, and the transition which requires lower energy, it must have higher lambda max value, because we know that energy is inversely proportional to the lambda max value or wavelength. So here, pi to pi star transition, N to pi star transition. If we arrange these four transitions, then highest energy is required for sigma to sigma star. Okay, then sigma to pi star, then N to pi star, pi to pi star, and first sigma to sigma star, then sigma to pi star, then pi to pi star, and N to pi star. This is the decreasing order of energy. Okay, so that means lowest energy required for N to pi star transition, and that's why lowest energy is required for N to pi star transition. That means it has the highest wavelength. So here, look at here, pi to pi star transition requires the wavelength which is less than 200 nanometer. But N to pi star transition requires the wavelength which is higher than 200 nanometer. So definitely our answer is B, N to pi star transitions. Okay. Now, then we consider question number 3. In the UV visible absorption spectrum of an alpha beta unsaturated carbonyl compounds with increasing order, with increasing solvent polarity. Now look at here. There are 4 options. N to pi star transition undergoes hypsochromic shift. Hypsochromic shift, that means absorption to a shorter wavelength. We can say that blue shift. Okay, pi to pi star transition undergoes bathochromic shift, that means red shift, absorption to a longer wavelength. So look at here, when we consider the polar solvent or when we increase the solvent polarity, then what happens? If the polarity of the solvent increases, then the non-bonding electron on the alpha beta unsaturated carbonyl compound, that means electron pair on the oxygen, what will happen? They are involved in the interaction with those polar solvent, which are involved lone pair. So as the lone pairs are involved in the interactions with the polar solvent, then what happens? Their transition will requires higher energy. Okay, non-bonding electrons are involved in the interaction with the polar solvent. That's why they require higher energy for their excitation. As they require higher energy, then their wavelength decreases. That means N to pi star transition undergoes hypsochromic shift. In the same way, pi to pi star transition, as the non-bonding electrons are involved in interactions, then in such case, pi to pi star transition requires lower amount of energy. Hence, it shows higher wavelength. That means it undergoes bathochromic shift. So our first option is correct. N to pi star transition undergoes hypsochromic shift, and pi to pi star transition undergoes bathochromic shift. Now, IR spectroscopy. So these are the 3 questions which I told you with respect to. First question is based on the lambda max value. Second, based on transition. Third is based on the solvent polarity. So remember that as the solvent polarity increases, the energy required for N to pi star transition also increases and its wavelength decreases. That means N to pi star transition undergoes hypsochromic shift, whereas pi to pi star transition undergoes bathochromic shift. Now, I have spectroscopy. Now look at here, in front of you, there is a chart which showing different functional groups with different IR frequencies. Now, what you have to do, you don't have to remember all these
Hello, sir.
IR values for the different functional groups. Don't remember that. Just memorize some important IR frequencies. For example, you just have to memorize the IR stretching frequencies for the carbonyl group, out of which amide has the lowest carbonyl stretching frequency, 1660 to 1680.
Sir, PPT is not visible.
Whereas the highest is recorded for anhydride, which has 1780 to 1830 centimeter inverse. I think you can see that here. Now, here double bond region is also there. Carbon sulfur double bond, carbon carbon double bond, carbon nitrogen double bond, and carbon oxygen double bond. Okay, so as I told you, carbon oxygen double bond, that means carbonyl group, and its frequency range is 1660 to 1830 centimeter inverse. Similarly, you have to remember some basic stretching frequencies of OH. If the OH of phenol or alcohol is there, then its stretching frequency ranges from 3300 to 3600. At the same time, if we consider the hydroxyl group of carboxylic acid, then it is somewhat broad, and its IR stretching frequency extends from 2500 to 3200 centimeter inverse. When we consider the hydrogen of alkyne, then what will happen? Is it visible to you?
No, sir.
Is PPT is visible to you?
No, sir.
Is it visible?
Yes, sir.
विजिबल हो गया
इसके लिए है नहीं। I think it is visible to you.
No, sir.
डिक्रीज
Is it visible?
Yes, sir.
Oh, yes, sir. Yes, sir.
यस यस
Now, so
Yes, sir.
IR spectroscopy. Okay. So here some basic functional groups with their IR stretching frequencies given in front of you. Now, what you have to do? You have to remember when you are studying IR spectroscopy, then you just have to remember this chart, which is in front of your screen. Okay. So look at here, IR spectroscopy, you just have to remember the IR stretching frequency of some important functional group, that's it. You don't have to remember any more thing out of this. And second thing, you have to remember with respect to IR spectroscopy is, what is the effect of conjugations and the ring size as far as the set exam or net exam is concerned. Look at it. As the ring size decreases, then what happens? IR stretching frequency increases. Okay, because as the ring size decreases, what happens? Strain in the ring increases, which increases the percentage of S character, and as the percentage of S character increases, minus I increases, and as the minus I increases, IR stretching frequency increases the frequency by approximately 30 centimeter inverse. Approximately 30 centimeter inverse. You just have to remember this. So look at here. On your screen, this is the cyclohexanone having IR stretching frequency for the carbonyl 1714. But as one carbonyl decreases, then it is increases by 33 units. Okay, 1747. Then again, when we decrease one carbon, then what will happen? Again, IR stretching frequency increases. Okay, so approximately it is increased by 30 centimeter inverse. So you just have to remember that as one carbon in the ring decreases, IR stretching frequency increases. Okay, now generally, what is the IR stretching frequency for ketone? It extends from 1680 to 1710 centimeter inverse, or you can say that 1680 to 1700 centimeter inverse. Generally, it is close to the 1700 centimeter inverse. So here, for 6-member ring, there is no angle strain. So the 6-member carbonyl compound has a similar IR stretching frequency similar to aliphatic carbonyl compounds or aliphatic ketones. Now, by getting this knowledge, that means what I have told you, you just have to remember the IR stretching frequency of some important functional groups, okay, such as OH, NH, NH2, okay. Then aldehyde carbonyl stretching frequency is there, COH, single bond. Then we have to remember all the carbonyl stretching frequencies starting from amides to anhydrides. Okay, now take a look at the first question from IR spectroscopy. Now the question is, among the following, the compound that displays an IR band at 2150 centimeter inverse is